You might wonder why in the last video I specified that some ionic compounds are non-electrolytes. You would think that most ionic compounds would dissolve in water, but it turns out that sometimes ionic compounds will be formed which are insoluble in water. And when that happens in reactions, especially when we start from a case where we have just everything being soluble in solution, when an insoluble compound forms, that is referred to as a precipitation reaction, because the insoluble compound then falls out of solution as a solid. And that's essentially just what it means to precipitate. An insoluble solid is formed by a reaction in solution. An example of this is when we take solutions of potassium iodide and lead nitrate and mix them together. So here in this glass we have the lead nitrate solution, and we add a solution of potassium iodide to that. Now both of those solutions are soluble, and we have the fully solvated iodide ion, potassium ion, lead ion, and nitrate ions. But when you mix them, what forms is that lead and the iodide ion combine with each other to form an insoluble compound. So lead iodide is not soluble. And as a result, it falls out of solution as this yellow solid. And so lead iodide would be termed a non-electrolyte since it's not soluble and doesn't break up to form ions in aqueous solution. So how do we know when precipitate might possibly form? How do we know when we might get an insoluble ionic compound? Well, thankfully, there are some solubility guidelines for ionic compounds that have been provided for us. Now, there are a number of exceptions that are listed here, but hopefully this will help us know and be able to predict when precipitation might occur and when to expect to see various things in when we mix ionic solutions in water. So here on the top, we have general examples for soluble ionic compounds. So essentially, we're looking only at the anions right here, and in this case, any compound that has a nitrate anion is soluble in water. Any compound that has an acetate anion is soluble in water. Now, also, any compounds that have halogen anions, chloride, bromide, and iodide here, are soluble, with the exception of just 3 examples here. If we have a silver cation, mercury cation, or lead cation, those are my 3 examples of exceptions to this, where the halogen compounds of these cations are insoluble in water. And then sulfates are generally soluble, with the exception of strontium, barium, mercury, and lead. Now, common insoluble ionic compounds, including those where the anion is sulfide, carbonate, phosphate, or hydroxide. So those are generally insoluble, with the exception of these exceptions listed here. So if my cation is an ammonium cation, that would be NH4+, any compound that has an ammonium cation is soluble. Any compound that has an alkali metal cation, that's the first row of the periodic table. So lithium, sodium, potassium, any compound that has an alkali metal cation is soluble. And then there's also some exceptions here. So these are generally insoluble counterions, but then if they have certain couples with the cation, if it happens to be a calcium, strontium, or barium cation for sulfides and hydroxides, those are generally soluble. So you might be scratching your head right now, and how in the world are you going to be able to keep track of all of this information, and particularly be able to put it together on a test or even just in our problem sessions? Well, hopefully I have a couple memory devices that may be helpful for you. On the soluble side, we can think of soluble as being Senga, or if you're familiar at all with Senga Nuna, she's a professional musician. And if you simply take the letters of her name, you can create kind of a memory device for this, for these soluble combinations. So sulfates, acetates, nitrates are soluble. And then group 1 cations, that is the alkali metal cations, shown here as an exception to the insoluble ones that would make them soluble. Ammoniums, that's shown here, that's an exception to the insoluble, so it must be soluble. And then halogens, that's shown here. Of course, there are some of the exceptions to the halogens and exceptions to the sulfates, but this will encapsulate most of the soluble compounds. On the insoluble side, it's a little easier to remember SPOC. So sulfides, phosphates, OH, which is hydroxides, and carbonates. Perhaps not spelled exactly as SPOC is spelled, but it should help you to remember insoluble compounds. Of course, there are exceptions to these, which we should have noted in the soluble side, but I hope that these two memory devices may help you in keeping track of solubility rules, because they do become very important, and we end up doing a lot with them as we go forward. So we must keep track of these. As much as you may dread it now, you will do yourself a huge favor if you can simply sit down and get these solubility guidelines in your head and practice them throughout the homework. So how do we take that? How do we take those solubility guidelines and then predict when a precipitation reaction may occur? Well, it's actually fairly straightforward. First, we note all of the ions that are present in the reactants. So on the left side of the equation, anything that we're starting with, we note all of those ions. And then we consider all of the possible cation and anion combinations, which actually aren't that many, because if we have two different ionic compounds, we only have two cations and only two anions. So there's really not that many combinations of cation with anion. And then we just check if any of those combinations are insoluble, because if any possible combination is insoluble, it will form. There's a driving force for those two to come together and fall out of solution. And so if any of the combinations are insoluble, then you can expect that a precipitation reaction will occur. So here's an example. Will a precipitation form, or will a precipitate form from mixing solutions of magnesium nitrate and sodium hydroxide? So first, we can just note the ions we've got present. We have nitrate ions. Remember, anything with a nitrate is soluble. So we have magnesium as the cation and nitrate as the anion. And and we can get the charges just from the periodic table. And then we've got sodium hydroxide, and sodium is, so hydroxides are normally insoluble, but sodium is a group 1 metal cation. It's an alkali metal cation, so it's soluble. So first, my reactant ions are just magnesium, and I apologize, this should be magnesium 2+, not magnesium plus, sodium plus, nitrate, and hydroxide. So I simply look at those and say, well, are any of those combinations insoluble? Well, there aren't really a lot of combinations. It's either sodium with hydroxide, which we already have, or sodium with nitrate, or we've got magnesium with nitrate, which we already have, or magnesium with hydroxide. Well, we already know that the magnesium nitrate and the sodium hydroxide that we start with are soluble. So we look at the other two combinations. Nitrates are soluble with everything, so this is soluble. But here we have a hydroxide compound that's with a non-group 1 metal cation. This is not an alkali metal cation. This is an alkaline earth metal cation. And so this would be an insoluble combination. So this is not one of the exceptions to the hydroxide insolubility. And so is any combination insoluble? Yes, the magnesium hydroxide is insoluble. And so I then simply write the chemical equation where I've got my two compounds here written as dissolved in water, aqueous. Going then to magnesium hydroxide, which is solid now since it would fall out of solution. And then I just add up the other compound that I must have is sodium nitrate. I just have to make sure that I balance the equation. And sodium nitrate is soluble, so I put aqueous symbols after it. Let's do another example here. Take solutions of iron sulfate and lead nitrate. And these are mixed. So will I get a precipitation reaction in that case? Well, my possible reactant ions are the iron 2+ ion. Now, how did I know it was an iron 2+? Iron is normally a transition metal. How did I know that it was 2 instead of 3? Well, I do know that sulfate, SO4, is a 2- anion. So I must have a 2+ cation. Lead, how did I know it was 2+? Well, nitrate is 1-, and I've got 2 of them, so it must be 2+. I'll look at all my possible combinations. Well, of course, iron sulfate, lead nitrate. Well, remember, all nitrates are soluble, so the lead nitrate and the iron nitrate must be soluble. And then sulfates are generally soluble, with only a couple exceptions. And one of the exceptions for sulfate is lead. So this lead sulfate would be insoluble. And so then I take just my starting materials, the iron sulfate, the lead nitrate, those are going to go on the reactant side. I'm going to write lead sulfate now on the product side with a solid symbol since it would be my precipitate, and then I just combine the other ions, which must be iron and nitrate, to give me the remaining compound, which is soluble. So I can write iron sulfate aqueous plus lead nitrate aqueous goes to lead sulfate as a solid plus iron nitrate aqueous.